Alright, so now I thought we'd take a little bit of time and discuss something that's fairly important in the world of computer science, and that's kind of a discussion about how do we really tell when an algorithm or a data structure we're implementing is actually, quote unquote, efficient, right? We could, as we've mentioned several times, there are many different ways we could implement a single abstract data type, right? Our stacks can be implemented with linked lists, or they could be implemented with arrays, and other more complex data structures can be implemented in a multitude of ways. But sometimes we really have to make a decision about what is a more efficient implementation over, say, a different implementation, right? And we need a way to throw actual hard metrics against that. And oftentimes it's kind of hard to do overall. We can't just necessarily run a program against this smaller data set and then say it took n minutes or n hours to run. Because as we feed larger and larger amounts of data into that data structure or that algorithm, all of a sudden the times it takes to actually run that full test to see whether it's going to eat up all of the memory in your system or whether it's going to run for 5 million years becomes rather prohibitive, right? We need some other more formal method in order to actually tell what or how efficient an algorithm is. And in order to do that, we have a couple mathematical ways we can go about looking at things. And the one we're going to be talking about and mainly dealing with in this class is something called big O notation. And all big O notation is just a mathematical way of describing how your function's going, the running time of your function. And it may not only describe the running time, but it could also be used to describe the memory footprint of your application as well. So it's kind of dual hone there. Oftentimes you can use this when you're judging memory versus space trade offs that you'll be making as you're writing your code. And you can also tell by kind of understanding or taking a guess about the size of data you're processing whether you need to create or attempt to create a more complex but higher efficiency algorithm versus a simplistic but rather low efficiency algorithm. And it kind of helps you gauge and judge those and help you make those decisions as you go. All right, so like I had mentioned before, big O notation is just basically a mathematical way of describing the running time of your function. And basically, big O notation is always going to start off with this polynomial function that you can kind of see an example of in the book. And this function is usually derived by effectively adding up all of the lines in your code and summing them up in this form, right? So a single line in your function or your program would equivalently be set to 1. So for instance, this program had some piece of code that had 5 single lines in it. Then it had some other piece of code where there were 13 lines inside of a loop. And then it had another piece of code where there was a couple nested for loops that would be run at least 7 times or have 7 lines of code in them. All right, so once we start looking at big O notation, we can kind of move it down into this second notation that you see here, which is just saying big O of 5 plus 13 times n plus 7 times n to the second power, right? And once we start looking at it in this notation, we can start applying a couple different rules to them, right? And the first rule is that if f of x is the sum of several terms, which in our case it is, right? Our big O notation is the sum of these three n terms, right? These three terms. When that happens, we basically drop all of the low order terms and we only take the highest order one, right? That's because as our input gets bigger and bigger and bigger, these two terms are going to have a diminishing effect on the actual output or of the actual running time of your program. The only one that's really going to matter, or the one that's going to dominate the runtime, is the highest order one, right? So for example, in our polynomial here, for any value n, our third term is going to be magnitudes larger than the other two terms, right? So summing them together really doesn't get us anywhere. And then finally, the second rule is that if the f of x has a term that is the product of several terms, which in this case 7 times n to the second power is, then again, just because of the magnitude of how the the multiplications and the powers happen, right? The n squared part is still going to take much higher precedence than the multiplying that times 7 part, right? So no matter what, once we start dealing with really large values for n, the multiplying it by 7 doesn't really change the magnitude of the number. It makes it larger, but it doesn't change the overall magnitude. So because of that, then we can go ahead and drop the 7 as well, which just gives us n squared. So basically, any function, any program that we can kind of simplify that overall polynomial down to will have a big old family of n squared. And generally, we say that any algorithm or any data structure that falls into the big O of n squared family will be equivalent. So any big O, any algorithm that is in the same big O family as any other algorithm is basically always going to be equivalent in time and space. Right? Of course, in real life running times, you might be off by a couple seconds, couple minutes, maybe even a couple hours. But again, big O is not meant to get you super specific time differences, but it's meant to at least kind of put you in the same ballpark so you can get a pretty good guesstimation of the running time and of the how much space your program's going to take up when it's running. Right? So, like anything else, we have a couple rules for determining composite functions as well. So, for instance, if your program is made up of a couple functions, that would be n squared, a couple functions that would be n, a couple functions that would be log n. These are kind of the rules that you can apply when you're trying to combine them together and give yourself the overall big O time of your overall program. Right? So effectively, there are just four examples, and they're all pretty simple. If you have some constant times some big O f of x, right? So if our function was n squared, you'd plug that in there. If our function was n, you'd plug it in there. In that case, you can just drop the constant, right? Because again, if we are multiplying the two, if you're multiplying the two times a constant, you can just drop the constant, because again, the constant does not affect the overall magnitude. If we're adding the constant, it has even less effect on the magnitude than it did in the multiplication instance. So again, we just drop it. If you are multiplying, say g of x times the big O of f of x, then the overall running time is just going to be big O of g of x times the big O of f of x. Right, so you just multiply g of x times big O of f of x, and it gives you a big O of g times f of x. All right, so for instance, if g of x was, say, n, or g of x was n squared, then your overall runtime would be n squared times log n, something to that instance. And then, of course, the same applies for if you're adding the two big O terms as well. Besides that, we also have, or I guess these really aren't rules, but this is just more an example of how the different big O families relate to each other. The most common big O families you're going to be working with are described here. Right, we have our big O of log n family, big O of n family, n log n squared, n cubed, and 2 to the n. Right, which of course, some of these are far worse than others. So for instance, we can just look at a given input, and then we can see how long that this would take at an algorithm or running against an algorithm with this big O time, right? So big O of n, for instance, is known as basically constant time, right? For each input, it's not known as constant time, but linear time. So it's more or less a 1-for-1 input-output. So for instance, if our input size was 10 with constant n time, this algorithm would take 10 picoseconds, micros, microseconds to run. And if we increase the input to 50, then our output would take 50 microseconds, etc., etc. And it just keeps growing at the same rate along with the input size. If we were doing n squared, for instance, then of course, if our input size was 10, then our algorithm would take 0.1 microseconds to run. And then if we increase the input size to 50, then we'd be looking at 2.5 milliseconds to run, right? And if we plug in our numbers and do our math there, so 50 to the second is 250, and you do the conversions for the seconds, and everything works out. So if you're given an input and you know one of the output families, then you should be able to determine how long an algorithm should take to run, or how much space an algorithm will take when it is running, right? Just by given your input size and what family of big O that algorithm falls in. And what's kind of fun to do is to kind of look at a graph of the different growth families to really get a handle on how these guys all look and how run. So for instance, I said that big O of n was linear time, right? So that means for every single input, we increase every single size we increase our input by will basically affect the time or space in the same manner. So if we increased our input size to 2, our size or space should be 2. If we increase it to 6, our time and space will be 6. Everything's growing at the same rate, 1 for 1. Whereas if we look at constant time, right, that means no matter how large our input size is, our algorithm will always take the same amount of time. Right? One example of that is array indexing. Whenever we index into an array, that is always going to take 1 unit of time, right? Because we have direct access to that array element. Whereas if we are walking a list, that's going to be a linear operation, right? Because as our list gets longer, we have more and more elements we need to traverse to either find something specific or to find the end of the list. And then, of course, times just kind of keep getting steeper and steeper, right? We have our big O of n squared time. We have 2 to the n. And if we want to get really crazy, you can have n factorial, which is really, really bad. As you can see, we get this just pretty much straight up spike, right? So by using this, you can kind of gauge and guesstimate how your functions are running, or how efficient your functions are or your algorithms are, by really just kind of breaking down your program and seeing and counting things and then applying those rules to see how your algorithm may behave with very large data sets. Besides the fun little graph, we also have some examples of what some of these families would look like in code, right? So for instance, big O of 1, that is how we represent constant time. That is, again, the one that for as large as, no matter how large your data set is, your program will always take, or your algorithm will always take, the same amount of time or space to run. All right, so for instance here, we just have a check: if x is less than y, return x, else return y. That is going to run the same amount of time, or take the same amount of time to run, no matter how many times you call it or what parameters you call it with. The second little piece of code here is a piece of code that's actually going to be big O of log n time. And the real key characteristic to recognizing a log function is when the input you're working with is being halved at some point, and the next operation you perform, you're only performing on 1/2 of the previous input, right? So for each iteration, the amount of data you're working on is getting smaller and smaller and smaller by half every single time. All right, so as you can see here, we have a while loop, and then the second line in our piece of code here just says mid equals high plus low divided by 2. All right, so this means high is going to be decreasing every single time. Or the other else statement says, well, help decrease high to make sure that everything works and is being halved correctly. Here we have our big O of n time, which is again just linear time. In this function we pass it some set of numbers, something we're looking for, and the key we're looking for as well. So we have a for loop that runs for as many numbers as there are in the list that were passed to us, and if we find the key we're looking for, we return the index to that key. Right? So even though we may find that key at the first run through this loop, we may find it in the middle of this loop, etc., it is still going to be big O of log n. And that is because our worst case, the utmost worst case, is when we have to go through every single element in that list in order to find the number we're looking for, right? That is basically the big O time for linear searches, right? Or traversing a linked list or searching an array for a specific value, right? With big O, when you're faced with those decisions about whether, well, hey, we could find it the first time, you always have to go with the worst case, which is we have to look through every single one of these in order to find the thing we're looking for. After big O of n, we also have big O n log n, which is log linear time. So you're basically multiplying the log time that we had before times some constant that's associated with the size of the input. And an example of that is merge sort, which is a sorting algorithm we'll be covering later. You also have big O of n squared time, which is quadratic time. Effectively, if you ever double your input, you're doing 4 times the work you were doing before. And a key sign for when you're dealing with a quadratic algorithm, or an n squared algorithm, is when you see 2 nested for loops and they are dependent on effectively the same thing, right? This outer loop is running on I less than number size, and the inner for loop is also running on j less than number size, right? So for every single element that's in the list, entire another set that's the same side of the count of elements will be running, right? So it's doing that, the amount of work you end up doing is 4 times what you had been doing if you double it, right? So that's our quadratic. Not great, but sometimes it's the best we can do. And then we, of course, have our exponential time, which, as you can see from the graph, is not a very good big O time overall, right? An example of that is this nice little Fibonacci summation we're doing here. Right, so that is kind of a quick little intro on big O. Before we stop the video, let's just take a little look at some of the functions we've already written and we kind of already know a little bit about, mainly the linked list functions, stack functions, queues, etc. Right, so if we were going to guess, let's say we had a linked list, and this linked list is only going to have a head pointer, right? What do you think what big O family do you think our prepend, append, and search functions would fall into? And hopefully, knowing what the big O families look like and knowing what this code looks like, it should be pretty straightforward and make a lot of sense. Right, so if we were looking at a prepend function with a head pointer, we know that our big O time should be constant, right? No matter how large the list is, because we're just adding to the front of the list, we never have to traverse it. So that means we always know where the head is and we can insert something at the front in a single operation, which is great. Whereas the append operation in this case would be big O of n. That's because we only have a head pointer, and now we have to traverse the entire list in order to find the end, and once we find the end, we can go ahead and append our new element to the end of the list. Okay, but this can be changed in your implementation, right? Because if we had a tail pointer, which a lot of our code has shown and has had, all of the sudden our append function also becomes constant time because we always know where the end of the list is, right? So that is one classic example of adding a little bit of complexity to your program, having it eat up a little bit more memory, but overall it has a very positive impact on your program's running time. Okay, that's just an example of some of the decisions we're going to have to make. And then, of course, search, because it's just a linear search, a linear walk of the list, will be big O of n, constant time. Or sorry, not constant, I always say that, but linear time. Okay, our stacks, again, a lot of this is going to depend on implementation, but in general, for stacks, our push operations should be constant, and so should our pop operations. And that's again because our push should just be a list prepend, and our pop should just be a list remove front, right? That's all we're doing. So because the stack is basically a special implementation of a linked list, we can just follow through and use those same operations that we used before and get the same big O time that we had. Okay, and the same is going to kind of hold true for queues as well in their enqueue and dequeue operations. But again, your implementation could have different effects on this. So for instance, our enqueue could be constant time if you had a tail pointer, or it could be big O of n time if you didn't have a tail pointer, or however you're defining your data structure. And then, of course, dequeue should pretty much always be big O of 1, depending on which way you ordered your list and which way you're looking at it and thinking about it. Okay, and then, of course, we have the priority queue, and this is the one that gets a little bit more interesting. Mainly because this one is very, very heavily dependent on implementation. So our enqueue could be 1, or it could be linear time, and so could the dequeue. One interesting thing about this priority queue, or the priority queues we're looking at right now, is that it's very hard to get both to be constant. Just because of the ordering rules we have to deal with, we'd either be sorting the list every single time we insert something, or we could be searching the list whenever we're removing something, so it's hard to get both. But later on in the semester, we'll take a look at another way to build a priority heap with a different sort of backing data structure other than a list, and it actually makes the overall big O time pretty reasonable, right? But we'll look at that later. Okay. But that is pretty much big O in a nutshell. We'll be looking at it quite a bit as we go through the semester, be applying the ideas to various functions and various other data structures we talk about. But if you have any questions, make sure to get a hold of me, and we'll get you fixed up with that.